Uh, Good day, everybody. Thank you, Professor Di for your kind introduction. And it's a great pleasure and privilege for me to open this Colloquia de 40 of the year 2025. So I'll be talking about seismic roulette today, and this in the recent years. And in the recent years, we managed to publish this book with Professor Pansa and Laor from Israel and another Benedetto De Vivo, also from Italy. So this book was dedicated to the memory of Vladimir G, who was my mentor. And the first chapter of this book was then elaborated in publication of this other series of papers called Seismic Roulette, Seismic Roulette, and now I'm thinking about Seismic Kaleidoscope. Science should be able to warn people of looming disaster. That's what my mentor was believed, and his trouble, as well as mine, is feeling of responsibility. So one could not argue that earthquake forecast prediction research requires from a scientist both a keen feeling of responsibility as well as a rigid control of claims and conclusions. Such responsibility requires further the highest standards of statistical analysis, because it is well known that improper use of statistical methods may lead to wrong, also to the user desirable causal inferences. So what's next for science? If science community continues to invent widespread and embrace myth about earthquakes. I would like to just to give you this series of comics, which were published first in June 2005, right after months after the Indian Ocean disaster and consequences. So this girl was in her conversation with talking horse, was explaining what is preconceptual science. And this is the one when you simply dismiss anything contrary to your conceived notions. And you can see that after some attempts for coming into discussion, the talking horse give up, while Danae says how easy it is to get approved. So she in the last slide of this sequence, Danae was asked how can she disprove the theory of gravity. And her answer was, that's where you come in. And so what's next for science if the populations of hazardous of areas have to get the have to cross the Raven in 2 jumps. So here are the two maps which were essentially endorsed by the International Lithosphere Program, by the United Nations International Decade for Natural Disaster Reduction. And it's the one which is sort of taking, continues doing the same thing with new available software and data. And this is the Earthquake Model Foundation is publishing interactive this global seismic hazard map. And now it's already a version of 2019. So here are the outcomes. Here are the contents. So this is the deadly earthquakes in Turkey, that called for 60,000 of fatalities. This is another one in Morocco. This claimed for about 3,000 of fatalities. Here is the earthquake in northwestern Afghanistan, series of strong earthquakes, which were also coming into the list of the top deadliest earthquakes of the 20th century. So this is the Noto Peninsula earthquake in Japan, was also disastrous and deadly, but not to come into the list. But nevertheless, the losses in the recent the quakes which I mentioned prove once again that G-sharp or jams 10% of exceedance in 50 years is inadmissible for any type of reasonable evaluation of seismic risk and making decisions concerning earthquake disaster prevention. The seismic differences sampled by epicenters of the deadliest quakes in the year 2000, since the year 2000, are mostly positive, with average and median of 2 units of MFI scale. So we know well that all models are wrong, but some are useful. But we often forget that many earthquakes are useless, and some are even harmful. So here's the list of the top deadliest earthquakes that happened since the year 2000. You can see that just 1 year added a number of new lines of about more than 60,000 of fatalities. You can also see here there's the differences between the observed and predicted ground shaking in the area. And you can see that the difference is about 2 units of intensity, which essentially at least corresponds to transition from strong ground shaking with light damage to poorly constructed buildings, cracks, and few instances of fallen plastic occur, to severe damage when when moderate or heavy damage is called ordinary substantial buildings with partial collapse, large cracks in the walls, forming cornices and chimneys. The table is sampled by the series of these deadliest earthquakes, but we made a comprehensive analysis and sampled by 10,000 earthquakes, strong earthquake magnitude 6, in the 23 years of this seismic history. And we find that these G-sharp and G-gem products appear to be harmful, surely not useful. And the non-usefulness can be just understood from the disclaimer of the website, of the GEM's website. So the information included in this map must not be used for the design of earthquake-resistant structures or to support any important decision involving human life, capital, and movable and immovable property. So apparently, GEM's GEM is not using data coming from earthquakes offshore, including the mega earthquakes in Indian Ocean and in Japan. As a matter of fact, 6 out of 24 magnitude 8 or greater earthquakes were not used for their determination. This restriction, compared to the sharp final map, reduces the test sample of strong earthquakes by a factor of 3 or larger, and formally the number of surprises from 30–40% to 20–25%. Still, this is a huge number, and the year 2023 has shown us how deadly could be this underestimation of seismic hazard. So it is worth noting that standard method of probabilistic seismic hazard analysis of the sharp and GEM is challenged by a methodology of neo-deterministic seismic hazard assessment. This new multidisciplinary scenario and physics-based approach for evaluation of seismic hazard takes advantage of the results of pattern recognition of earthquake-prone areas and intermediate-term earthquake prediction of different spatial accuracy, which are tested to be reliable, realistic, and useful evaluation and mapping of apparently time-dependent seismic hazard and associated risk. The deterministic physics-based earthquake scenario modeling is now gaining momentum in spreading worldwide a paradigm of reliable seismic hazard assessment that eventually should change the minds of scientific and engineering communities from the common pessimistic disbelief in past forecast prediction abilities to the challenging issues of realistic predictability of natural hazards. So here I would like to cite the famous mathematician of one of the great authorities in mathematics of the 20th century, Israel Moisei Gelfand, who was who in his memorable lecture was mentioning that it is terrible that in our technocratic age we do not doubt the initial basic principles, but when this principle becomes the basis for constructing a material or finally developed model, the model is viewed as a complete substitute of the natural phenomenon itself. And the better the model, the worse it becomes for the applications. Indeed, the pressure of snatching initial principle will lead us to use the model well beyond the possibility of its application. Unfortunately, this is the case of probabilistic seismic hazard assessment. So what do we know about earthquakes? The extreme catastrophic nature of earthquakes is known for centuries due to resultant devastation in many of them, and you can see some of the year 2023. The abruptness, along with apparent irregularity and infrequency of earthquakes occurrences, facilitate formation of a common perception that earthquakes are random, unpredictable phenomena. And many people, including scientists, do not distinguish between unpredictable, random, and haphazard, which distinction is crucial for scientific reasoning and conclusions aimed to reducing impacts from disastrous earthquakes. seismic evidence per se rejects hypothesis of random recurrence of earthquake. This spatial predictability of earthquakes is evident. The boundaries of tectonic plates are clearly defined by seismicity, particularly intense in subduction zones. A broad band of seismicity extends from southern Europe to Southeast Asia, associated with collision zones between the Eurasian and Arabic, African, and Indian plates. So you can see here two maps which were plotted in the year 2000. And one of them provides the annual number of magnitude 4 large earthquakes during the period from 1964 to 1995. And on the right, you see the maximum observed in 1 degree by 1 degree cell in the same period, much larger period from the year 1900 to 1997. So the map on the right can be already a good example of for assessing seismic hazard. And right now we are working on it, just making some, adding some new information we have. And so earthquakes are cell similar, and they obey the unified scaling law that generalizes the Regretfully relationship, accounting for their fractal properties. So A, B, and C are a little bit more than A and B values of Gutenberg-Richter relationship. In particular, the expected annual number is now depends on the linear dimension of the area you consider where you count. So earthquakes are not random, but rather haphazard. That is lacking any obvious principle of organization. So mathematically, the characteristics of such a haphazard, apparently chaotic system are nevertheless predictable, but up to a certain limit and after substantial averaging. So here you can see in the lower part, you can see this earthquake forecast prediction accuracy classification, and many consider temporal part of it, distinguishing long-term, intermediate term, short-term, or immediate predictions. However, forgetting about the spatial accuracy, which could be long range up to 100 source zone sizes, to middle range, narrow and exact when you pinpoint the source zone of event. And also don't forget that Gutenberg-Richter law suggests limited magnitude range to prediction to about 1 unit of magnitude. Otherwise, the statistics would be essentially related to the two denominating smallest earthquakes, which are not that important in hazard assessment. So earthquake forecast prediction is not an easy task that implies a delicate application of statistics, and regretfully, in many cases of seismic hazard assessment, the claims of high potential of the method are based on a flawed application of statistics and therefore are not suitable for communication to decision makers. So far, none of the proposed short-term frequency signals showed sufficient evidence to be used for a reliable precursor of catastrophic events. Sorry. The famous yes of Gardner and Knopov to the question, is the sequence of earthquakes in Southern California with aftershocks removed Poissonian, is based on an assumption of random Poissonian distribution for the occurrences of main shocks violating the main principle of statistics, which says if a statistic falls in a reasonable part of the distribution, you must not make the mistake of concluding that the null hypothesis is verified or proved. That is the course of statistics, that it can never prove things, only disprove them. Regretfully, many researchers are misled by rather popular mistake of concluding their model verified and proved when a test statistic falls in a reasonable part of distribution. Applying probability uncertainty epistemic or aleatory error estimate does not guarantee getting adequate results when automatically using the data and the best statistical procedures available. It is evident, particularly in seismology, that not all uncertainty can be convincingly represented as a probability, and all probabilities can be well estimated. This is true even in the systems that are rather well described by theoretically correct probability models. Earthquake-related observations are limited to the recent most decades or centuries in just a few cases, of which Italy is one of the best available data. And that is why probability estimates by probabilistic seismic hazard analysis remain subjective values ranging from 0 to 1, usually derived from analytically tractable hypothetical models of seismicity. Making seismic hazard assessment claims either terms or time-dependent, quantitatively probabilistic in the frames of the most popular objectivist viewpoint of probability requires a long series of yes-no trials, which cannot be obtained without an extended, rigorous testing of the method predictions against real observation. So, what can we get in testing? So the set of errors, the rates of failures, and the alerted space-time volume can be easily compared to random guessing, which comparison permits evaluating the effectiveness of the method and determining the optimal choice of parameters in regard to a given cost-benefit function. These and other information obtained in such simple testing may supply us with realistic estimations of confidence and accuracy of seismic hazard assessment, forecast predictions, and if reliable but not necessarily perfect, with related recommendations on the level of risk for decision-making in regard to engineering, design, insurance, and emergency management. It is evident the necessity and possibility of applying simple tools of earthquake prediction strategy, which was developed by George Moulton, and possibility of applying simple tools, in particular, error diagram and seismic roulette, null hypothesis as a metric of alerted space-time volume. So here you can see the error diagram from the original publication of George Moulton, just a little bit modified. You can see here this gray area of the predictions that are possible with the given set of information. And you can see also this gamma curve, which was called by Moulton error diagram, and I prefer using this name. And you can also see explanation why this gray area is concave, and why any strategy has this opposite one, alternative opposite. And you can also see a number of different say, cost-benefit functions, gamma, and the optimal strategy, Q star, is given for the maximum of the percentage of relative space time, or percentage of failures to predict. And this Q star gives you the optimal choice for this function. So here is another part of the couple. So this is seismic roulette, and I noted that it was first demonstrated a long time ago, especially in the beginning of the year 2000 and earlier. And this is a simple way, and very nice, in my understanding, the analogy to the seismic roulette statistics, which were known since Blaise Pascal. So just consider a roulette wheel with as many sectors as the number of events in the sample catalog of earthquakes, a sector per event. Then make your bet according to prediction and determine which events are inside area of alarm, and put one chip in each of the corresponding sectors. Then nature turns the wheel and makes the outcome of your prediction. And if seismic roulette is not perfect, you will systematically win or lose. And as I already mentioned, there is an alternative antipodal strategy, which can make your prediction efficient so that you will win and systematically and outscore the losses. So here is the theoretical, say, explanation of what I mean. And in fact, at present, we consider a direct product measure of space-time alert. There is a very more general case of time-space dependent measure for future, more sophisticated null hypothesis. So a practical recipe of using new measure is associated with statistical significance of prediction method is as easy as 1 to 3. So take a reliable sample catalog of earthquakes and count how many events from it are inside the territory considered. This will be your denominator. At a given time of regular prediction updates, count how many events from the catalog are inside the area of alarm. This will be your numerator. Integrate the ratio over the time of prediction experiment, and the result is an estimate of P to be used for with the achieved predicted versus total target earthquakes in computing the significance of predictions. So I have not much time, so I'll just focus on the two cases. One is the West Pacific short-term forecast of shallow magnitude 5.8 earthquakes in April 10, 2002 to September 13, 2004. And this is Jackson-Cargan-Jackson, this method, which was advertised, and thanks Jan, I was getting this information on each update of this map. And on the right side, you can see the maps of the global testing earthquake prediction algorithm M8 and M8 MNC. So here is the outcome for the Western Pacific short-term forecast of earthquakes, and which arrow diagrams show that underlying method is deficient for prediction of aftershocks. You can see that the outcomes for the two counts are as far away from the random guessing. However, when the aftershocks are removed, the situation changes completely, and you can see that it is pretty much random. So this is the case. And here is the results, the same error diagram for the predictions by M8 and M8 MSC algorithm since the year 1985, and since the formal start of the real-time experiment that started in July 1991. So you can see that the predictions for magnitude 8 or larger events is far outside, so we are sort of confident that the results are not random. And we see that in prediction of magnitude 7.5, we are not that far from the confidence, 99% confidence. So here is the performance in the table, and you can see that out of 101 magnitude 7.5 or larger events, 43 were predicted by M8, and for 1/3 of those, the prediction was, the algorithm was able to reduce the area substantially. So you can see the confidence, which is 99% for all of them, except for combination of M8 and MSC algorithm in the real-time prediction model, which may be due to the fact that not everywhere MSC can be applied, and that could be the problem. So the results of truly global 33-year-old real-time experiment are in direct confirmation of the illicit common features of both the predictability and diverse behavior of the Earth's naturally fractal lithosphere. The statistics achieved prove with, I would say, seismological certainty, with confidence about 95%, rather high efficiency of M8 and M8 MSC predictions limited to intermediate term, middle, and narrow range accuracy. Here is one example, and this one was first. This prediction was first announced at the UN World Conference on Disaster Reduction, and was essentially on the 20th of January 2005 in Kobe. And the title of this statement was December 26, 2004, greatest Asian earthquake, when to expect the next one. And the last slide of 3-minute plenary was stating the following: all 4 mega earthquakes of the 20th century happened within a narrow interval of time. Such a cluster is unlikely with 99% confidence for uniformly distributed independent events. Since good evidence suggests that seismic events, including mega earthquake cluster, it is possible that we will have further confirmation of the prediction within 5 to 10 years in other regions. This prediction was eventually confirmed by the mega thrust offshore Maui, Chile in 2010, and then by the mega thrust and tsunami of the Pacific coast of Tohoku in 2011. So an opportunity to reduce the impacts from this mega earthquake was missed, while the primary reasons for not using the prediction for improving preparedness in advance of the Tohoku earthquakes include inadequate links between emergency managers and the earthquake prediction information, and no practicing application of existing methodologies to guide emergency preparations and policy development on how to make decisions based on information provided for intermediate-term middle-range earthquake prediction and limited but known accuracy. So that is at all conclude that M8 and M8C algorithm predictions, although limited to intermediate-term span of years and middle-range location of 1,000 kilometers, can be used to reduce future disasters. Nowadays, the problem of widespread scientific raises might be due to misuse of statistics beyond the possibility of its application in many disciplines due to superficial education as a tool for exercising in numerology by counting descriptive, although politically desirable parameters, lots of mechanical application of available software, and the tutorial policy of many scientific journals. However, we know now that seismic roulette is not perfect, and therefore seismic hazard assessment and earthquake prediction planes can be useful for reducing future impacts from disastrous earthquakes if reliable, but not necessarily perfect. Seismic roulette is a game of chance. Disastrous earthquakes are low probability events locally. However, in any of earthquake-prone areas worldwide, they recur with certainty, that is with 100% probability sooner or later. Nature spins the wheel and throws disastrous earthquake balls, and we can win the game if we take a chance to play systematically. Okay, how to win at seismic roulette? Here is one of the last slides of presentation. In India, the multi-state preparedness campaign mega mock drills prove that the impact of potentially disastrous earthquake can be mitigated if a low-key preparedness measures are adequate and timely. As a matter of fact, the government and population of Himalayan kids and planes have put already their first bets on seismic roulette and achieved a successful response of all agencies involved. In particular, clear understanding that if the mitigation and preparedness measures are adequate, the impact of any great earthquake can be contained. As a proactive measure to enhance emergency response capability, in India, now, since the year 2020, a proactive measure to enhance emergency response capability provides a practice of conducting mega mock drills focused on earthquakes and associated hazards as systematically carried out. Therefore, eventually India is to win at seismic roulette game. Always the thing that, yeah. So I guess that is. So, well, the conclusion is a simple one. The confirmed reliability of pattern recognition results, along with realistic and positive neo-deterministic scenario-based modeling and testing against reality, allow concluding that nowadays science can disclose natural hazards, assess risk, and deliver this state-of-the-art knowledge of looming disaster in advanced catastrophes, along with useful recommendations on the levels of risks for decision-making in regard of engineering design, insurance, and emergency management. Thank you.
Thank you very much, Vladimir, for the almost optimistic talk. And are there any questions, remarks, suggestions from the audience? So I don't see any.
I have a question.
I have a question. So Giuliano, you can ask the question.
Yes.
Okay, go ahead.
Volodya, I think you mentioned a sentence that can be taken very seriously, but maybe people can understand it in the wrong way due to the fact that there is a lot of use of the concept of a return period. And you've said the earthquake recurrent with certainty at 100%. So you use the word recurrence, but then you made the correct correction at any time. What do you think? How to try to remove from the general behavior the fact that the return period have a meaning? Because what you say is that the return period do not have any physical meaning. And I think this is a major problem that we have to face in earthquake prediction in general, because the mantra is to say that earthquake cannot be predicted, full stop. And I think that you proved that earthquake cannot be predicted with ultimate precision, and that is a totally different story. Also in practical terms, because administrators, if they get from experts or so-called experts, earthquake cannot be predicted, full stop, they don't have to work on this kind of attempt to do what you clearly described. If people will understand that the earthquake cannot be predicted with ultimate precision, then they are obliged to do something. And that is a change in paradigm that I think is badly necessary. What do you think?
Giuliano, I think I was not using period throughout the text, but recurrence. And
Yes.
in particular, this strong disastrous earthquakes in the places we are prone to will recur with certainty sooner, which means that, you know, even if you consider that those are coming randomly following Poissonian law, that will mean that, say, like in Kamchatka, in the next 70 years, plus minus 70 years, which means tomorrow is a possibility. And the probability in Poissonian model is always the same for a certain interval of time, for one day in particular. So I think on the other hand, I was trying to show that earthquakes are not, earthquakes do cluster. So the prediction which was made at the UN Conference on Disaster Reduction and was claiming not only a made possibility to be applied for mega earthquakes of magnitude 9, but also to the observation that the mega earthquakes of the 20th century happened within 15 years. So the first mega earthquake was suggesting that if those clustering, then we should expect in 10, 15 years, a repetition of this, a repetition of what happened in the 20th century. And it happened. And moreover, M8 was able to pinpoint the occurrence of this magnitude 8.8 in offshore Maui in Chile. And it was also predicted, say, with a little bit missing of the time, or just 2 months, the occurrence of this earthquake, mega earthquake and tsunami in Japan in the year 2011. So earthquakes do cluster. And moreover, we know that there are foreshock sequences, and the case of not a peninsular event is also very characteristic in this sense. So scientists were discussing this swarm of activity at the Noto Peninsula. They have already conferences of what does it mean, but they never look ahead thinking that swarm is precursory of a large catastrophic event, and that did happen. Similar to what happened in Aquila, by the way.
Yes.
So it was also a swarm, and everybody were sort of fascinated with it, but they were not thinking that this is a precursor of a big event, which was in effect confirmed by historical evidence in Italy by itself. So did I answer?
No. The question was to use the word, to use the concept of recurrence, reoccurrence or reoccur. Just simply say occur, can occur. Earthquake can occur, certainly, because we are floated by return period concept, which is, I think, misleading.
No, I was never using return period.
No, I know that you were not using that, but you used the reoccurrence, and I think that it can be enough to say occur with certainty. Period. You know, to avoid, because people is affected by return period. People think in terms of return period, not as you said, clustering in the more complicated process that you described, and that is important. I think we have to remove a wrong paradigm from the general society. I think, but that's a minor thing. What you said is much more important. You said that the earthquake cannot be predicted with precision, with ultimate precision, and that's important because people to say that it can be predicted, but they believe in return period, and this is conflicting, conceptually conflicting, within which politicians and administrators, they have this plenty of space to navigate and do nothing for earthquake attenuation of hazard. That's
Yeah.
my
Fully agree, because what the recommendations of this Hyogo meeting in Kobe and the Sendai meeting in Sendai region recently, they are essentially speaking of the same, although are separated by 7 years. Yeah. So the one was in 2005. So the second one was in 2011. So it was also to commemorate this earthquake in offshore Tohoku. So and And by the way, this year, and just in a few days, there will be 50th anniversary of the earthquake in Haicheng, which was the first and unfortunately the only case when earthquake was predicted and with an effect of saving lives and so on. And of course, nowadays we have a much more information to make this prediction first very broad one, and then narrowing it down to the occurrence of the event. So unfortunately, I don't know. So in China, in 1975, there was a cultural revolution, and people were sort of mobilized to make observations, which I'm not sure is possible nowadays. Maybe with the smartphones, which we all have, and which are sort of accelerometers, by the way. So that's the...
Okay, other questions? So I don't see. No. So I think we should. I thank the speaker very much for the very. Sorry.
I think that. Excuse me. I think that there is somebody who tries to say something.
Yeah, Antonella Peresa. Yeah,
Thank you so much.
she raised the hand, but physically I didn't see that.
Yeah, I couldn't raise the hand, the virtual one.
Yeah, sorry, go ahead.
Just to support the conclusions of Kossobokov, I just would like to remind the results that we got for Italy in about 28 years now of rigorous prospective testing of forecast methods based on pattern recognition scheme. The uncertainty is pretty large, but so far we got 11 events out of 14 forecasted by a specific algorithm, which is called CN, and the probability to get similar results by chance is below 1%. So the confidence level is very high, and that's, let's say, really a unique experience supporting the possibility of forecasting earthquakes. So for sure we can do better in future, but we have this, let's say, this evidence based on results collected in 30 years. It takes time, but I'm also positive. I support the conclusion of Volodya. Thank you.
You know, in 2005 at UN conference, I was presenting structure and nonlinear dynamic group of the Abdul Salam International Center for Theoretical Physics. So this was NGO I was sort of representing it. And I was given those, say, 3 minutes for prediction that megaquake may happen. So I guess that these lectures, which were giving at the workshops on linear dynamics and earthquake prediction in Trieste, at the CTP, were very good in spreading the notion that earthquakes are not random, predictable, and we can do these predictions effective, and we can urge people in advance of disaster. So I fully agree with Antonella that there are other algorithms, CM in particular, and those require, like M8 and CM, these algorithms require testing, at least retrospective, to get some measure of reliability and measure of confidence in the claims that arise from those algorithms. Yes, the claims from CN are highly confident, so it's about 99% as well. So that's what makes us optimistic. However, we are confronted with this, with opposite of members of preconceptual science application.
Yes.
So I think, are there any more? Giuliano, do you see anybody? No, I think so. I can close and thank Voloida for the very stimulating talk. And I give you the, we adjourn to next month with Regretfully Spilantini, who looks that is giving us some hope also for the Parkinson disease. Have a nice week and see you next month. Thank you.
Bye-bye.
Bye-bye.
It's Chinese New Year. This is 2 weeks to do it. Thank you for giving this opportunity, and bye-bye.
Bye-bye. Bye-bye.